the previous speech. I didn't, at least. So, this session is this is the last session of today. So, what can we learn from the long temperature record of Uppsala? And first, who am I? Or who am I? I'm an electrical engineer from the beginning, then a software developer. And in general, I question what people say and claim, so I'm skeptical. Ingmar looks skeptical to what I'm saying, so then you're a true skeptical if you're skeptical to someone saying that he or she is a skeptical. I started to write programs to analyze temperature records in 2013. And I've been writing on the klimatupplysningen.se for about 10 years. And when doing this writing, I came in contact with Lennart Bengtsson. Lennart Bengtsson is a former professor in meteorology. You can tell that I'm not a meteorologist because I can't pronounce the word. But together with him, we wrote a paper in 2014. It took us 2 years to get it published because the reviewers were super picky on non-important things in this article. But finally, we made it through after several rounds of reviews, and it published in this scientific paper Tellus in 2016. The article had the name Assessing Atmospheric Temperature Data Sets for Climate Studies. I need to write it down because even I can't remember the name. But the main conclusion was that the atmospheric records and the ground records of the temperature, they don't match. And there is still no explanation of this. So this was one of the most read articles in Tellus at that time. And then I'm also the chairman of Klimatrealisterna. It's we who have organized this conference. Or Ingmar has organized the conference, mostly.
Together.
90%. So, now I'm going to talk about Uppsala. You could think that I live in Uppsala because I talk a lot about Uppsala, I write a lot about Uppsala, but I don't. I've been there maybe 10 times. But this guy, Anders Celsius, he lived in Uppsala. Uppsala is, by the way, one of the university cities. In Sweden, it's about 1 hour north of Stockholm. And I mean, you know him, everyone, because he invented the Celsius scale. But a fun fact is that he put 0 degrees at the boiling point and 100 degrees at the freezing point. But after his death, they turned the scale around. And after his death, they also renamed the scale from the centigrade to the Celsius scale. I think it's still called the centigrade scale in some parts of the world. He was a professor of astronomy in Uppsala. But his predecessor, Burman, he started with temperature measurements in the 1720s. And after his death in 1728, Celsius took over. And he didn't do all the measurements himself, but he had so-called observers doing the measurements. And thanks to Burman, Celsius, and many others, we have one of the longest temperature records in the world from Uppsala. And it starts in 1722. Another less famous person in Uppsala was Åke Sundborg. He was a geographer and he did urbanization measurements. UHI, that's Urbanization Heat Island. I think most of you are familiar with this concept. It means that urbanized areas, they have much higher temperature than surrounding rural areas. So this guy, in 1948, late 1940s and early 1950s, he drove with a car with a thermometer across Uppsala. And he showed that even then, that the temperature inside the city could be several degrees warmer than outside. And he did a very thorough work, and his results are still valid. So he was one of the pioneers here. now let's go to this Uppsala series. This is a reconstructed yearly temperature from Uppsala by Uppsala University. So, two researchers, Bergström and Moberg, they have done a great job to put together the old measurements from Uppsala. Because at least in the beginning they made the measurements on different places. So I think they have done a pretty good job to put all this together, and they published this in the beginning in 2002, I think. But you can see at the end you have this very scary red area where the temperature has risen a lot, but unfortunately this is not true. This does not represent the rural area, because they haven't learned what Sundborg did, his research in the 1950s. And here is the proof for that. This is the place where they measure the temperature today. It is next to their premises. That's very convenient. And you could think that this is an AI-generated image, but it's not. This is the truth. They measure the temperature next to their premises, next to a big intersection, and next to 2 parking lots. So, and you can also see that the paint on this station, it's bad. So you will probably get some warming from that also. But if you look at the city of Uppsala, this is from Google Maps. Up until 1853, they did the measurements inside the city. But at that time, the population was 8,000 people only. But then they moved the site to what is now the old site here in this picture. And that was fields outside the city, open fields outside the city. And now you can see that the city has grown, and it has grown around this area, and this is now called the Observatory Park. But due to vandalism, the Uppsala University were forced to move the site. But they didn't move it outside the city. They moved it further inside to the place where I showed you before with the photo. And there is actually a much better site outside Uppsala at Uppsala airfield. And this is an old military airfield. And they started with the regular measurements, both day and night. I think in the beginning it was 4 days every day, 4 times every day. And we have continuous measurements since the 1950s from Uppsala airfield. So, but why doesn't the Uppsala University use the data from that site? I don't know. It's not their site. It's not their data, probably. But we can use this and create a better Uppsala series. We replace the Uppsala city measurements with the Uppsala airfield measurements from 50s and onwards. Of course, we need to adjust this data a little bit because it's not done at the same place. You need to add a fixed bias, monthly bias, to match the old measurements. And you can find the methodology and data available on my homepage. I will talk a little bit more about that at the end. So, using this methodology, we create the better Uppsala series. I'm not using these scary red colors, right? But does this look scary? Maybe it's a little bit hard to read the smaller, the small numbers. But around here you have 1850, 1900, 1950. So you can clearly see the last little ice age culminating in the 1950s-60s. You can see this very abrupt warming in the 1920s and 30s. and you can see the recent warming. And you had this period of cold weather during 1960s. So this doesn't look that scary, right? And when we now have this better Uppsala series, we can do some analysis on it. Maybe this is not the perfect data, but it is at least much better than what Uppsala University provides. And have done comparisons with nearby rural stations, and this series have a much better correlation with the rural data. So, then we come to the question, why do we have all these fluctuations? And in order to find that out, I've used data from something called the ERA5. I don't know if you're familiar with that, but that is a reanalysis set from the European Center for Medium Range Weather Forecasts. Basically, they use the weather models to recreate old data. They are filling in the missing gaps by using the weather models. So they take all the measurements they can find, feed them into this model, and then you get new data, which is like a compromise of all the measurements. But you also have data with the gaps for the wind and cloud cover and many other parameters. And now they have extended this to starting from 1940. I don't think that the early data is super reliable, but it's still very interesting data to work with. And then I also used solar radiation measurements from Stockholm. Stockholm is like 70 kilometers from Uppsala. But in Stockholm, at Stockholm University, they started with these measurements in 1983. So irradiance, that is radiation per square meter, you can say. That's how much energy that hits the ground from the sun. And I also used the data from the North Atlantic Oscillation Index. I don't know if you're familiar with that, but this index is basically the difference in air pressure between Portugal and Iceland. If you have a high index value, it means that you have a low pressure area around Iceland. And when you have a low pressure area around Iceland, we get warm winters in the Nordics, because the wind blows from the Atlantic, it's from the west and the south, and pumps in warm air to our countries. And in the opposite, if you have a low index value, then we have a high pressure area around Iceland. So, then something about statistical correlation. This is the p-value. I think you've seen some of this in previous slides also. That's the null hypothesis test. A small p-value means that there is a correlation between two data sets. And I will use this to show the correlation between the parameters and the temperature. And then you have the R value, which shows the linear correlation. So you can have a low p-value, which means you have correlation, but also a low R value, which means that you have a low linear correlation. Then you have some other kind of correlation. But usually in these kind of data sets, you have more or less a linear correlation. So, if you didn't understand this, it's not so important, but instead we go to the correlation with the temperature. We can see from the winter that we have a very good correlation with the wind from the south. Everything here in green shows a good correlation. And also wind from the west. And this North Atlantic Oscillation Index. Of course, they correlate to each other also, because when we have a high North Atlantic Oscillation Index, we have a strong or higher wind from south and west. So, for the winter temperature in Uppsala, and maybe Sweden, and Norway, I don't know, is controlled by where the low pressure areas are located in the Atlantic. For the spring, it's not as clear. You can see that the R value is a little bit lower. And I think the spring is like the battle between winter and summer. But then for the summer, it's a completely different story. The summer temperature has a very high correlation with the radiation from the sun. That means the energy that hits the ground from the sun controls the temperature. It seems quite natural, but the winds, they are not. So they have very low correlation for the summer temperature. And you can also see that the cloud cover, it has an R value which is negative. And that because a low cloud, if you have less clouds, you get a higher temperature. But if you, so it's the opposite from the actual radiation. And then we go to the autumn, where we have a good correlation with the wind from the south, but wind from the west, it has a poor correlation. I can't explain this. But this is also that the autumn is like a combat between the summer and the winter. So now I'm going to show you some plots. I have a lot of plots. I'm going to only show you some of them, as examples. So this is how good the correlation is with the winter temperature and the North Atlantic Oscillation Index. The index is in blue and the temperature is in red. You can clearly see how when you have a warm winter, you have a high index value. When you have a cold winter, you have a low index value. And this goes down all the way to 1860s. So basically we can explain the winter cooling and the winter warming more or less totally by this index. When we had the less good data from Uppsala University, then we couldn't see this clear correlation. But when we have good data, we get this good correlation with these very simple measurements. Then we go to the spring. As I said, it's not as clear for the spring and not for the autumn either. But this is the wind from the west as in blue and the temperature in red. There is still a correlation, but there are probably many things together that affects the spring temperature. And the spring is defined here as March, April, May. So there could be different conditions also in these different months. Then we go to the summer. Unfortunately, we only have data from 1983 for the radiation. But here you can see the very good correlation with the radiation from the sun in blue and the temperature for the summer in red. And as you see in these graphs, the radiation from the sun has increased by about 30 watts per square meter. Compare that with the effect from the CO2.
Do you know what the reason for this is?
The reason, I would say, is mostly for less clouds. So this is the summer cloud cover and the temperature. But I can't explain why the correlation is not as good with this data. Maybe there are uncertainties with this data because this is, like I said, this reanalysis data. It is a compromise by many factors. But there could also be an impact of less aerosols. But there has definitely been less clouds also. So, yes, it is hard to tell, but I think the radiation measurement, they are direct measurements. They're very clear that we have got about 30 watts per square meter more radiation in the summer. This is not as clear. Then we go to the autumn. I have another type of plot. It's a scatter plot. On the x-axis you have the North Atlantic Oscillation Index, and on the y-axis you have the temperature. You can see that when you have a high index value, you have a high temperature. But there are other things affecting the autumn temperature also. So, some conclusions. We have a very strong correlation between winter temperature and wind from the south. And we can explain the recent winter warming by low pressure areas around Iceland. We have a very strong correlation between summer temperature and solar irradiance. And in principle, less clouds cause more sun hitting the ground. But it is not as clear for the spring and the autumn. But we know that the wind from the south and the west, it has a clear impact. So, if you make some further conclusions, that all or almost all of recent warming can be explained by natural factors. And the natural factors dominate the temperature fluctuations. And the global warming is just seen as noise in this data. And since natural factors dominate, the temperature might go up or go down in the future. I don't know. Who knows? Of course, this is not. Is this representative for the globe? No, of course not. Is it representative for other places on the earth? Probably. But Uppsala and Sweden, Norway and Finland, we should be affected most by the global warming. And still, the global warming can't be seen in the data. So, that was my conclusion. Thank you. And if you want to read more, you can go to my homepage. On my homepage, you can find also the link to the TELUS article I talked to you about. You can find an article with a climate model using the seasonal variations of the hemispheres, where I calculate the climate sensitivity to be around 0.3 degrees. You can also find an analysis of the raw data from ground measurements compared with these global data sets, GISS and HADCRUT, if I pronounce it correctly. And maybe you will be disappointed, but I can't see that they have adjusted the data at all, basically. There is a super good correlation with the raw data and the result. I think they have adjusted the data too little, in fact, because they haven't made barely any adjustments for the urbanization effects. So, thanks a lot.